The title of my talk will be interactive decision making in multi-agent intelligence systems. Yeah, so as the title suggests, the main focus of my research is the decision-making problems that I encountered in multi-agent systems. Here, by multi-agent system, I refer to any computer-based system that collect, analyze, and respond to data from multiple sources or multiple devices. This could range from things like smart grid, Internet of Things, connected vehicles, all the way to different types of recommender systems that provides those different digital services that we are using on a daily basis. And so currently, a large portion of the tasks being solved in multi-agent systems are being solved by supervised machine learning. What supervised machine learning does is saying, given some fixed data set, how do we train a model that can minimize some prediction loss on this fixed data set? And the successful applications of this include image classification, speech recognition, or machine translation. However, in my research, we argue that for some applications, at least, there is actually a feedback loop, making supervised machine learning a less desirable choice of the learning paradigm. For example, typically for those real-world intelligence systems, with the predictions made by the supervised machine learning model, we want to use that to make some predictions to interact with the environment. And then from this interaction, some new data points are collected, which will be added back to the data set and then used to improve our model estimation in the future. So examples of this include the things like clinical trials or recommender systems, where this data collection is affected by the decision making in this intelligent systems. So the consequence is that the ID assumption that is crucial for supervised machine learning theory is no longer holds. And moreover, for this type of applications, the data needs to be collected from the actual interactions with the environment. In clinical trials, that means the data set has to be collected from real patients. For recommender system, that means the data set needs to be collected from the actual users of the recommender system. In this case, it's very expensive to conduct such experiment to get those data points. And what this hints is maybe it's desirable to do this in a sequential manner. We do this through interactions with the environment. And the idea of doing this sort of a sequential sampling over fixed site sampling dates back at least to the 1940s. And this seminal work by Robbins in 1951, they also provide a pretty strong argument that why interactive decision making is more sample efficient compared with fixed site sampling. In the applications example we saw in the previous slide, fixed site sampling simply means we will conduct some uniform random decisions. We will recommend uniform random items to the user, or we will conduct some uniformly randomly chosen treatments to patients to collect the data, which is very expensive in this case. And they also laid on the idea of measuring the quality of the sequential decisions through regret, which we will talk in more detail in the following slide. So to be more specific, we are considering interactive decision-making problem that looks like this. Every time that agent makes some decision, which is denoted by XP, then the environment will immediately provide a feedback denoted by YP. And we assume this feedback is generated by some unknown reward function, which is denoted by X plus some stochastic noise. So using the recommender system example, in this case, the unknown reward function is simply capturing the user's preference, which is unknown to the recommender system, but we want to learn it through interactions. Feel free to interrupt me if you have any questions. And regret is defined by the difference between the reward of the optimal decision and the reward of decision chosen by the algorithm. So xt star here denotes the optimal decision at time step t, and the xt is the decision chosen by the algorithm at that time. So what this objective suggests is, in order to minimize the regret, we want to finally pin down actually what is the optimal decision, such that this value will be 0. So that suggests we need to sufficiently explore the whole decision space in order to find the xt star. And for most interactive decision-making problems, sublinear in time, the whole length of time horizon is desired. So on top of the challenges of this exploration to find the optimal decision, for multi-agent systems, we also have some additional challenges. The first challenge is that apparently the decision space is now much larger than the single agent setting. Using this super simple illustrative example, we have a multiple robot trying to navigate this maze to find the treasure. We need to make decision for every agent in this case, and also because each agent is in a different location or in a different environment, their task, which is captured by the app, the unknown function f in the previous slide, that can be different across agents, and that can also be different over time. So in this case, the research question is how do we identify which clients can help each other, they can collaborate with each other in an online manner. The purpose here is to improve the sample efficiency so they can collaboratively complete their task. And then another challenge is for many multi-agent systems, the agents are actually decentralized, which means doing this kind of a centralized decision making is no longer feasible. We cannot simply ask everyone to upload all their observations to a central location and then do the model estimation and then compute all the decisions on in that central machine. Instead, we have to move the both model estimation and the decision down to each agent, and then they will only collaborate with communication. So the purpose in this line for this in this case is how can we design algorithms such that this agent can collaboratively minimize regret while making sure the communications they require is slow. And also for multi-agent systems, there could be some pretty complicated relations or behaviors among the agents. For example, we may have some agents that have a private agenda. It has a slightly different objective with the others, and they are unwilling or they have some intrinsic concerns in collaboration. In this case, we need to design some incentive mechanism to incentivize the clients to actually collaborate with each other by sharing their observations.
So this is like a standard reinforcement learning formulation for multi-agent, or this is different? Like, what is this?
Yes. So it's quite related to standard. I guess when you say standard reinforcement learning, you're talking about multi-agent IO.
Yeah, I mean, you have these actions and reward and
yes.
environment, right? That's what you just said.
Yes.
So they instead of one, just have one agent, now you have multi-agent or something. Like what's a big picture? Where does this fit in?
So this is captured by multi-agent IO. This is we can say this is a specific case of a stochastic game.
So in order to solve this problem, not necessarily one has to use the reinforcement learning. You can use something else. Or you have to be reinforcement learning.
Sorry, can we solve this challenges?
Yeah,
using something other than reinforcement learning?
Yes.
I would say no, because this is already we can classify this as a reinforcement learning method already.
Yeah, so this is a reinforcement learning.
Yeah,
right?
it is reinforcement.
So what's the difference between this and standard formulation of reinforcement learning? It has one agent and standard,
right?
Reinforcement learning here is multi-agent.
Yes.
Is that the only difference, or there's some questions?
That is the only difference, but because of that difference, a lot of things change. The objective will be different.
Yes, so it's a multi-arm bandit problem, but extended to the multi-agent setting,
yes,
right?
Yes,
So you have new challenges that you want to address.
that's right. That's right.
Yes.
Yes.
So this is okay. So, but again, multi-agent reinforcement learning have been around for like 15 years, 20
Yes.
or something.
That is right.
So I guess at some point you have to show where your work
Yes.
starts.
Exactly. So that's right. It's we are basically working on multi-agent reinforcement learning, but from with a different perspective, we consider different challenges. Yeah. Okay. So this is a slightly even more specific formulation for what we are working on. At every time step, we assume every agent. In total, there are capital N number of agents, and then each one of them will make a decision denoted by XTI. Then the environment will return some reward of YTI. And we mentioned that we want to minimize the regret that is incurred by all the agents in this system. So here is where I mentioned this difference. In most of my research, I work on bandit problems, so no state transition involved. That's where I said why I said the general multi-agent reinforcement learning is a general concept than what I did here. But the bandit problem itself has a pretty broad applications. For example, in recommender system and in sequential experiment design. In those cases, you just don't have a state transition. But most of the results in my work can be directly applied to some subclasses of episodic Markov decision process. Basically, the real challenge or bottleneck is the same. It's also exemplified in my problem. So, for example, if we generalize my setting to the Markov decision process, then this decision X is no longer some action. It's a policy that we choose at this particular episode, and then this function F is a value function of that policy. So, and my result directly applies to cases like Markov decision process with the so-called linear function approximation. So yeah, so my research is multi-agent reinforcement learning, but focusing on different problems. Any questions about this slide?
Yeah, that's right.
Yeah, then let's move on. So as an answer to the challenges mentioned in the previous slide, my research considers how do we find the optimal decision via this collaborative decision making in different situations. So the first one, as we mentioned, the tasks solved by the agents can be different and they can change over time. So they are heterogeneous and non-stationary. In this case, we designed algorithms that identify which agents are solving related tasks in a dynamic manner and let them collaborate in this online environment. And on a second direction, we mentioned that they can be decentralized. So the focus in this line of research is how do we design communication strategies such that they can cooperate with as few communications as possible. And on a third direction, what if the agents are self-interested? So they won't just collaborate when the system designer asks them to, because they have some private agenda. They will only agree to collaborate when they find that collaboration actually helps them. So in this case, the focus in this line of research is to design such incentive mechanism to enable the collaboration. And for the first part of my talk, I will focus on this second direction where we design communication strategy for decentralized agents. And we term this line of research as federated bandit learning because of its close relation to federated learning in supervised learning paradigm. Okay, so now we mentioned that in this problem, the objective is to minimize regret over all the agents and want to ensure low communication costs. And motivating application scenario of this is federated recommender systems. So nowadays we have increasing concerns about privacy. So people don't want to simply send their data up to some central server. So instead, we want to make sure we have a decentralized data storage and the decentralized model activation over millions of edge devices. And in this case, communication is critical. So oftentimes, the communication becomes the bottleneck of your model training. Yes. So as a illustration shows here, we consider this star-shaped communication network. So there is a central server, and then there is some edge device, which is basically our phone or computers. And in the recommendation system scenario, each of these mobile device, they will run some recommendation app. So every time step, they will make some recommendation to us, and then we will respond by something like a click or didn't click, or we watch the video or didn't watch the video. And here to make for the sake of simplicity in this talk, I assume all the agents share the same unknown reward function. That means they all share similar preference. But our paper actually considers a situation where their reward function can be different. Okay. So this is the motivating example. And then we mentioned just now that this is closely related to federated learning in the supervised machine learning literature.
Is this equivalent to being able to pull multiple arms at the same time step? Because each one is going to get one of those.
Yes, that's right.
Products.
Yes. So each agent can pull an arm, and then they will get new observation. Yes. So yes, that's exactly the difference compared with the federated learning, because in federated learning, we assume the data sets are fixed. It's just that they are decentralized to different devices. But in both cases, we want to emphasize the communication efficiency. Yes.
I have a question.
But the difference is that in our case, the data set is growing over time on everyone. Since as we consume the contents recommended by the app over time, the data set they collect from us is increasing over time, and that is the key difference from this offline federated learning, because that means over time you want to know when you should update your model such that you make sure your model is still relevant with this increasing data set.
Yeah, so I think I asked you this on the breakfast, so that's still not clear to me. So in this case, you're saying the recommending system, each copy of the recommended system, each client has, right?
Mhm.
They will use their data to find out what movies they like and so on. Right?
Yes.
So then what are they communicating? They're communicating something which you want to preserve. What are they communicating?
Yes. So okay. So for the offline federated learning, they're simply communicating gradients or some local models.
So the model is being updated, trained at the client, at the server or something.
Oh, so both in our case, both the client will upload the updated model locally, and the server will also update the model.
Mm-hmm.
So because the purpose is to save communication,
Yeah.
so when the local model gets new data, it will just use.
So this recommended system is being updated as the user use,
Yes.
and they will send these gradients to the.
Yes.
Okay.
Yes. Okay, we can move on. Yes. So yes, and then this is exactly the question: what and when the agents should communicate in order to collaboratively minimize regret. And to answer this question, we need to look at what's the typical way of minimizing regret in a centralized setting, where we just have one agent, all the data are located in a single place.
So again, in this, the recommending system is the reinforcement learning based system.
Yes.
Okay. So you have reinforcement learning based recommending system, and now it's a federated learning, and it's been trained, and
Yes.
so these clients need to send the gradients
Yes, but not only gradient, because the objective, we'll talk about the.
Some of that things also.
Yes, yes, so, okay. So in a centralized setting, to minimize regret, we typically resort to the principle called optimism in the face of uncertainty. So what it does is we first, the x-axis here is my state. This is everything I can recommend to the user. And then here, this orange line is my estimated model based on the data I already have. And then in order to minimize regret, we need to construct confidence sets such that this confidence set will contain the unknown reward with high probability. So this blue curve here represents the true preference of the user, which we don't know. And this orange line is what we know by learning from the data. And we need to construct this set denoted by this two gray curves, such that the blue line is covered here with high probability. And then the optimism principle says, in order to minimize regret, at every time step t, we need to pick the arm or pick the item that has the highest upper confidence bound, basically this point. We can clearly see that this point, this is definitely not the optimal choice, because under the true reward function, the true mean reward of this choice is actually very low. And this the red dot x star is actually the optimal choice, which is decided by this unknown function f star.
Can you turn on your speaker here, maybe, or we turn on the other one, because there's a question and we have both speakers muted.
Yes. Okay.
Yeah, can you hear me?
Yes, I can hear you now.
Okay, excellent. I think it was on slide 12 or 13. You had the architecture you were studying, and I wanted to clarify that the agents you had, I think it's this one, So the agents you have are not talking to each other, right? They are all, deciding on their communication with the central server or the coordinator, correct?
Yes. Yes.
Okay.
So this is a star-shaped community. Okay. So the question is, are the can the agents directly communicate with each other? And the answer is no. They can only communicate through the server.
Okay. Thank you.
Okay. Yes. Then okay. Let's move on. Yes. And then according to our regret definition, then by making the choice xt, we incur regret, which is this distance, which is basically the mean reward of the red dot, which is that at this red dot, and then the mean reward of the choice we made, which is the green dot. With the optimism principle, we guarantee that this regret is upper bounded by this distance from the highest point, which is this black dot, the upper confidence bound, and then the lower confidence bound here. So this is the pretty much all those optimism-based reinforcement learning algorithm. Their regret is upper bounded in a similar way as this. So the cumulative regret is simply bounded by the summation of this confidence bound over time. And what this tells us is we know the regret depends on how fast the volume of this whole confidence set shrinks over time. So by volume, I simply mean the area of this gray region. If we make sure this gray region shrinks fast enough over time, then we can prove a desirable rate of the regret. And what this tells us is in order to collaboratively minimize regret with n agents, what we should do is we will use the volume of the confidence set as a proxy to minimize regret. So the agents should instead collaboratively try to minimize the confidence set volume. And how do we do so? Okay, now in this decentralized setting, every agent has its own confidence set. So each agent will construct something like this. And we denoted the confidence set of client I at timestamp T at VTI. And we just mentioned in the previous slide, collaboratively exploration of the decision space means joint estimation of the confidence set. So what they should communicate in this case is some statistic or learning parameters used to construct this confidence set. And this is related to what we mentioned just now. We won't simply use gradients because that's not enough. In federated learning, we are only concerned about having a good model estimation on fixed data set. So communicating gradient is enough. But for bandit problem or reinforcement learning problem in general, we instead need to communicate things that help them construct a confidence set. That's how they can coordinate with each other in terms of exploring this unknown decision space efficiently. The intuition is that if someone already tells me he has already tried this option, then as another agent, upon knowing this, the agent shouldn't explore that option anymore. Someone already tell you that option is bad, and then I should explore something else. And in order to make this process communication efficient, we should instead only communicate when we find out that the volume of the content set has changed sufficiently enough, meaning that some other agents find out that it has collected so many useful data, it has a string-based confidence volume so much that it should share that knowledge with the others, so the others won't waste their time exploring things that are already known by this agent. So this is a design principle of this whole line of research. And moreover, in this federated environment, in practice, agents can have a varying computation and communication capabilities. So which means sometimes you have an agent or an edge device that is super slow in terms of communication or in terms of computing the model updates. So then in this case, one question we consider is how do we be robust against such stragglers? We want our whole learning procedure to not need to wait for such a slow client. Instead, it will just go on without waiting for everyone in the system to finish the task. So we want to update the model whenever we receive a communication. Any question with everything so far? Okay. Yes, and then to address these concerns we just raised, we propose an asynchronous communication framework. So what this does is at every time step, some agent denoted by IP, they interact with the environment. Basically, a mobile device make a recommendation, and we have provided it with a feedback. Now it has collected some new data points. Then we will design some event that measures whether the volume of this agent's confidence level has changed sufficiently enough. If it has changed a lot, then this agent will share everything it has collected so far. Basically, the statistics used to construct this smaller confidence set, it will share that with the server.
So in this one, so agent is the person watching on the cell phone some movies or something.
This decision will be made by the cell phone.
Yeah, so cell phone, that agent is using the recommendation system.
Yes, right.
And you look at what movies you should watch or something.
Yes, right? Yes, exactly.
And then you are saying, what can you explain what is collecting, which you send to, you would make a decision to send it to server. What is it?
Okay, yeah. So at this point, I'm trying to be general, and later we'll see like specific instance of the algorithm. So let's say we just run. We will see later. Let's say we just run a linear regression, a ridge regression to estimate the user preference. We use a ridge regression to fit the user's history data. Let's say that's our model. then what we will send here is the statistics used to compute the ridge regression model, which is the matrix and a vector.
Yeah, but I mean, that's nothing to do with the reinforcement learning, right? So I thought you were saying that there's a reinforcement learning recommendation system the user is using. So
Yes.
Is it?
So this is already reinforcement learning because of this exploitation.
Okay.
Yeah.
I see.
Yes.
So, but that, when you do regression on this particular agent, it's not just specific to this particular agent, right?
Mhm.
But I thought you have the bigger model which is being shared with all other.
So a bigger model will be here on the server, right?
Okay, so that it will fit the regression model to all the agents or just?
Yes. So we already made the assumption that everyone is solving exactly the same task.
Okay,
Yes.
I see. So
Exactly the same task.
Yes. So in this
reward function.
reward function is same,
okay,
but they don't have to be. In my paper, we have an extension that consider different situations, like everyone can be slightly different from each other. So aggregating their data together brings you more benefit compared with the harm done by the implicit bias. So on another work, we also mentioned earlier that we assume users are passive. So we assume that there are millions of users, but their behaviors may only follow a relatively small different types. Some people just like, yeah.
so this example you gave, which is good regression one, say, let's say you do the regression on agent IT.
Yes.
And so you will decide whether you should send it to the server or not.
Yes.
Right?
Right.
And that decision made it has changed significantly or something?
Yes. This confidence set, basically the knowledge it has collected.
Okay.
Has increased.
So then you send to server and then what? Other agents are also send to the server the same kind of information or something?
Okay, so that won't happen like simultaneously.
Yeah.
Only the agents find out that they have collected enough new data will upload to the server.
Oh, I see.
Yeah.
So then there will be a one regression function for all agents, or there will be separate regression function for each agent?
One regression function for all agents. Yes.
So this will assimilate whatever regression function parameters this guy gave with all others and do one general model or something?
Yes. The server will just aggregate all of them together to have one regression model.
Okay, good.
So that's exactly what the server does. Server will do something similar. Server will think, look at this event, whether what I have now is sufficiently different from what I told the agent in the last communication. If it has changed a lot, meaning the server has much better model than that agent has, so the server will download this new model to the agent. Okay, so this is the design principle of this asynchronous communication framework. Yeah, and then we already mentioned this. So when we use a linear regression, I need to remove faster. So for linear regression, the confidence set is simply has a form of an ellipsoid, and then this ellipsoid is constructed by a matrix A and a vector B. We just mentioned that as well. Therefore, what agents communicate is simply their local updates denoted by this delta A and the delta B. Basically, this is the difference between the A matrix the agent currently has minus the matrix that the agent had at the previous communication. If this difference is sufficiently different, so this difference now will be measured by the determinant of a matrix. Yeah. So with this asynchronous communication framework, we can show that with the proper choice of the okay, we didn't mention this, but we have a two threshold that controls. We can see here that controls this is the threshold that controls how often I should upload, how often I should download. With proper choice of these two thresholds, we can show that we can attain the optimal regression. Optimal in the sense that this is a lower bound in the centralized setting. our performance can be as good at moving all the data to a central location to train one single model. Meanwhile, we only require communication that is sublinear in terms of the whole time horizon t. So what we mentioned just now, if we do this centralized computation by moving all the data together, the communication cost of that, which is measured by the number of times of communication, that will be dn squared t. So we can see we have a reduced linear dependence on t to log n t. And we
Can you remind me again, what's D?
Oh, d is the dimension of the feature.
Of the features, okay.
Yes, n is the total number of agents. Yes. Okay. So I guess we can quickly go through. So the proof idea is basically what we mentioned just now. We to prove this, we can attain optimal regret. We can do that as long as we guarantee the confidence ellipsoid volume of one agent is always not that different from the confidence ellipsoid volume of imaginary centralized agent. Basically, we consider there's some imaginary agent who really has all the data in the system, and it can.
So maybe since you don't have much time, you can skip the proof code.
Yes, we're short on time. Yes. Okay. Let's. Okay, and then here's a simple simulation results illustrating what our algorithm can do. By changing the threshold, we essentially this controls how much communication we need, and this blue dots correspond to our algorithm, and here the x-axis is the communication cost, the y-axis is the regret. So for both values, lower value for both regret and communication, lower value is desired. So basically, the closer it is to the origin, the better the algorithm is. Yes. So here, what this simulation shows is that we can attain a relatively close regret to the imaginary centralized agent while only requiring communication costs that's several magnitudes lower than that centralized algorithm. Yes. Okay. So apparently there are some limitations of that work we just introduced. In reality, what if the linear function fails to capture the underlying mapping in the data? Then in one extension of this work, we consider the case where we generalize that to a generalized linear model, so that it covers the Lorenz regression and the Poisson regression. And then we also consider the situation how do we do this with kernel method. In this case, all the agents, they want to collaborate with each other in searching some unknown function in the reproducing kernel field space. And in the most recent work we just submitted, we want to move even closer to what is done in practice. We want to have something that's a generic nonlinear function, like a neural network. And in this work, we only assume that this function can be non-convex, but we only assume at a small neighboring region to the optimal position, it is strongly convex.
So can you give intuition what's again this function is about what? What is the function?
This is just in reality, people usually use neural networks, right? So that is can be non-convex.
No, but what's the function? The linear function was about what? What is the intuition?
What goes in, what comes out.
What comes in, what comes out. Here the input is just I recommend what item I recommend, and what is the output is what the user responds.
So your recommendation is what it's a one hot coding or what?
Oh, it's it's just any feature vector describing it could be a real value vector.
So it's a pre-constructed feature vector
It's
of a entity which you can have a preference over.
Yes. So you can imagine this can be some embedding that in industry people use to describe their item that they train through some super large models to get some embeddings from this super complicated neural network view set for the subsequent tasks. Yeah. Yes.
So you have some So you have an embedding of a movie,
Mhm.
which, and then you are expressing preferences over it, and your assumption was your original assumption was that the human's preferences are a linear combination of that.
Yes, of that
feature.
embedding. That's right.
But
Then the
is it
big
meaning
thing would
say that like we're saying the linear in what sense? That there's a one axis of preference,
Mhm.
other axis is some embedding of a movie.
Mhm.
What
Linear,
does that mean? I mean, why is it linear one to one?
linear in the sense that so this X is the feature of the item. This data is we believe the reward is generated by the inner product between X and some unknown vector data.
But that's basically you have like a huge neural network,
Mhm.
and the interesting part of the neural network is in the embedding,
Yes,
and then you just take the very last
yes,
step of the neural network, and that one you push it to
Yes.
the users.
yes, that is right. That is for the previous one. So in the later, what we said is that we are moving like further away from linear model. So there can be some non-linearity, or it's a still linear function, but it's linear in a kernel space. Or now in this work, we are saying, okay, this doesn't have to be linear. It doesn't even have to be a convex function. We only need to be strongly convex within a small local region of the optimization. For the others, this can be any smooth function. Yeah, we can move on. We have 14 minutes. I think should be enough. So just now we mentioned for those applications, so like a recommender system. In this case, the agents are simply edge devices, mobile phones that runs the recommender app. In this case, these agents are called altrusive, means they will share data when the central server asks them to. But in another application scenario, when these agents are actually like a standalone organizations, this organization as a whole, they are trying to solve some problem by this interactive decision making, and these different organizations want to collaborate with each other on solving the same problem. In this case, they may not be willing to share data when some algorithm asks them to. So in this case, we need to design a mechanism that can incentivize those agents to communicate with each other. In our recent work, we have the behavior model of those agents. We assume is that these agents are willing to share as long as they find out that the benefits provided, the benefit due to collaboration outweighs some potential privacy risk. In that case, these agents will be willing to share. And then we want to, in this work, we design this incentive mechanism such that we still attain the optimal regret result in the previous slide, while having a relatively low cost in terms of the incentive provided. So now we are ready to move on to the second part of the talk. Just now, what we are talking about is we only consider the interactions between our recommender system, let's say a platform like YouTube, and the users. So, and we design different decision-making algorithms such that this platform can minimize the regret in its interaction with its users, meaning it can quickly identify what items each user likes over a very short period of time. But what we and here we implicitly assume that the content space in the YouTube example, basically the videos, this content space is static, or it won't be affected by the decisions made here. But oftentimes, we also have some other strategic agents in this ecosystem, which are the creators of such contents. Their decision in terms of what contents have been produced is in fact affected by the decisions made in this in this interactive decision-making process. So this completes another loop where the interactive decision-making actually has a broader impact in this whole ecosystem. So specifically in this second part of the research, we are interested in the question like from a game theoretical perspective, how the welfare of these users will be affected by this content creation process. Will be more specific in the later slides. So what exactly is the impact we are talking about? So we can think of it in this way. Through this interaction with the user, the platform can learn the true user item relevance. It can learn that unknown function f we mentioned earlier. Now that the server knows what every user like, what the user does is simply makes recommendation based on this learned relevance. It will simply recommend whatever the user likes most. But the consequence of that is this will induce shifts in the consumption distribution of the contents. And this has been widely recognized in the literature about the recommender system. So for example, let's say the user population forms groups, and there is a majority group that likes certain types of contents. Then what the recommender system does, what it does is the item or content that satisfies the needs of this majority group will receive a much higher exposure to the population. This is a direct consequence of a relevance-based recommendation. Then the contents that are preferred by the minority group will get much lower exposure. Then this is what we call a tyranny of a majority, because in the applications we just mentioned, like YouTube or Instagram, many of the content creators, they are revenue seeking. The reason they make content is they want to make some money. So if they find out that certain types of contents will receive much lower exposure to the population, then they will simply switch their focus. They will start making different types of contents that are more popular. And this will cause the whole content space to become more and more homogeneous over time. And this potentially reduce the social welfare as the minority user groups' needs are just neglected. And the research question we want to ask here is whether this competition among the content creators can lead to worse social welfare, and how we can improve it. Yes. So this is the problem formulation that we have. We mentioned we now, in addition to platform and user, we also have content creators, which are strategic agents as well. Now, in our problem formulation, each creator, it will choose some pure strategy. Here, the pure strategy basically means a particular type of content. Every creator will choose to make some type of content, and then together, this content is denoted by S. This S is the set of all contents provided by the content creators. And then upon receiving the set S, the platform, it will present a subset of contents to each user did. Like a platform will choose the most relevant contents in this set S to each user. Then we assume each user is associated with a feature vector xj. This feature vector basically describes the user's preference. Let's say this can be constructed using some demographic information or some history data. Then what the user will do is, upon observing this list of contents recommended by the system, by the platform, this user will just pick one constant from this set based on its true relevance. Plus some stochastic noise. The noise is to capture the fact that when human making decision, which content or which item I want to choose, there is some stochasticity in that. Then after the whole process, the platform will simply will also pay the content provider according to some payment rule denoted by PI. So intuitively, this PI depends on things like how popular these contents provided by the creators are among the population, how relevant those contents are. Yes, and then yes, we can move faster here. So apparently, this whole procedure will repeat itself over and over again. And what we care about is the kind of average the outcome, how good how good this whole dynamic is in terms of social welfare. And that's why we introduced adopt the notion of the force correlated equilibrium. So the reason is that if we assume each content creator is strategic, it is running some no-regret algorithm. It's actually running some no-regret algorithm means it will run some smart algorithm. It will make some smart decisions to actively maximize its payment. If the content creator is doing that, then the empirical strategy distribution, basically the empirical distribution of its contents will converge to this so-called CCE, force correlated equilibrium, and then we will study whether this converged CCE is good in terms of social welfare. And we measure how good, whether social welfare is good or not, using the concept of price of anarchy. So this is a quite intuitive concept. On the numerator, what it says is if, let's say, if the platform can dominate the content creation of every content creators, basically YouTube, if YouTube can exactly controls what each YouTuber produces, then it can choose the optimal set of contents to maximize the social welfare. That's what the numerator is. That's the optimal social welfare possible. And in the denominator, what we have is the social welfare corresponds to this empirical distribution, which is empirically what we will have when the content creators are running are like adapting their content generation strategy. Yes. So what we want to do is we ask the question how the payment through PI of the platform can affect social welfare. And in practice, there are two ways of typically two ways of deciding this payment. One is based on the exposure. By exposure, basically this means how often each content creator's contents gets consumed by a user. That's the exposure. And then in this case, we show that this payment based on the exposure is actually a bad idea. The ratio between the optimal welfare versus the welfare of under this particular payment rule, there's no upper bound of that. It can be much worse than the optimal. And in cases when the platform only recommends the most relevant content to user, this ratio can be arbitrarily large. So, and another commonly used strategy is to pay the content provider based on the user engagement. So intuitively, engagement means so the item gets consumed by the user and times whether the user actually likes it. So you can imagine something like maybe this content looks super eye-catching. It tricks people to click it, but actually after clicking it, this content is kind of mediocre. It doesn't really, it's not so relevant to the user. In that case, this engagement will be relatively low, but the exposure can be relatively high. And here what we say is if the platform actually pay the content creator based on engagement, based on the quality of the these contents, then we can prove the social welfare in this case can be upper bounded by 2, meaning the final social welfare that the content providers converge to will not be so far away from the optimal social welfare possible. And in simulation results, we show we validated this idea where the orange and the red curves above are corresponding to the payment strategy based only on the whether it's eye catching or not, and then the purple line and the green line down below here is the social welfare. The POA value with corresponds to the payment strategy that pays by the satisfaction level. Yes, and then this is a summary of the topics we mentioned just now. Yes. So in terms of so any questions so far?
So this equilibrium is something similar to the Nash equilibrium, right? In which
Yes.
you look at only unilateral deviation of one of the content creators, right?
Yes, yes. So this covers the Nash equilibrium. So because in some cases Nash equilibrium may not exist, but the cross-correlated equilibrium always exists for finite games.
It's because you're taking an expectation.
Yes, yes, exactly. Yes. Okay, so then we can talk about the future directions. So I think a short-term future direction of my research is to actually push the adoption of my new learning paradigms in real-world applications, since that's the main contribution we are making in our lab. And then to do so, we have been actively developing toolkits of those federated bandit algorithms in this open source project. And then we also have been collaborating with the industry, with Instagram specifically. We are running this social welfare optimization algorithm on Instagram to do the online test. So pushing the benefits of pushing this new learning paradigms to practical application scenarios that we can identify new problems, and then that helps us improve the algorithms and problem formulation to make it actually usable or relevant to practice. And then on another related direction of my research is enhancing the privacy and security issues. So what this is, so there are several. Okay, so compared with the standard privacy and security for supervised machine learning or federated learning, is that we saw just now, we have a much more complicated ecosystem here. So one possibility is the content creators, they may want to collude with some adversary, or they are themselves adversaries, so that they want to actively shift their content creation to manipulate the platform, either to gain more revenue, or just simply want to chase out all these competitors. So this will bring out a lot of new formulations of this privacy and security problems. And then as a long-term direction, I also want to further dive into the fairness part of this whole research. Just now, we were more about thinking from the item side fairness. By item side, we mean whether this contents or items exposure to the user population is fairly distributed. But we also saw just now that this item side fairness actually affects the user side fairness, because the content creation, if the content providers are not treated fairly, that will cause change in the whole content space, which will limit the choice of the platform, which further affects how the users are treated. We saw just mentioned that problem with the tyranny of majority example. So that exactly says the user's fairness are affected by that. So this is also quite an interesting future direction. Yes, and those are my collaborators, advisors, and community members. And this is a reference mentioned in this talk. Okay, thank you.